This week we are continuing our discussion of bivariate statistical tests, which we call these tests you would conduct, usually just one of them, as a preliminary test of your hypothesis. In other words, your prediction that one variable, an independent variable, is going to affect your dependent variable or an outcome. So moving on, we talked last week about the chi-square test and how you would use that if you have two categorical variables. This week, we're going to be talking about t-tests and different types of t-tests. We use t-tests when you have a categorical independent variable. So if your independent variable is nominal or ordinal and your dependent variable is interval ratio or continuous, then you would use a t-test. A t-test is a two-population test for a difference between means. And we can talk about a difference between means because the dependent variable is continuous. So you would be able to calculate a mean for your dependent variable. Generally speaking, there are two types of t-tests, the independent samples and the dependent samples t-tests. You should know the difference between these. And it's just like when we talked about statistical independence and statistical dependence last week, it's similar logic. So with independent samples, the selection of items or objects into one sample did not affect and was not affected by the selection of items or objects into the other sample. So if you're comparing men and women, if you're comparing liberals and conservatives, if you're comparing students versus non-students, anything like that, you're going to have independent samples. Having a group in one sample had nothing to do with who was in the other sample. They are completely independent of one another. Dependent samples are when you have the selection of objects or items in one sample either affecting or being affected by objects in the sample side, in the other sample. So you might have, there are a couple of different dependent samples that your book talks about. One is matched pairs, and I go over this in methods for those of you who had me. We go over it when we talk about experimental and quasi-experimental designs, so it doesn't get a lot of attention, but hopefully it'll ring a bell now that I'm discussing it again. Matched pairs occur in quasi-experimental designs. So in true experimental designs, you have the two groups, a treatment group and a control group, and the researcher has to, and this is in true experimental designs, the researcher has to randomly assign. So a researcher has a sample already, and they have a treatment and a control group. So they take their sample and they randomly assign people from their sample into either the treatment group or the control group. So let's say if I'm using my class, one of my classes as a sample, and I'm trying to test for the effect of something. Let's say I'm going to test for the effect of a study session. So I take my class and I randomly assign students into the treatment group, which would receive a study session, and the control group, which would not. That's random assignment. So I take my sample, randomly assign, meaning everyone has an equal and known probability of falling into either group. But I don't choose based on like GPA or gender or anything like that. I just would pick a number out of a hat. If you get a 1, you go to the treatment group. If you get a 0, you go to the control group. Oftentimes in our discipline, researchers cannot randomly assign. So one strategy they use to try to simulate random assignment is called a matched pair design. And that is where you create a second sample to be similar to the original sample based on one or a few important characteristics. So let's say that I'm looking at, let's say, juvenile transfer. You can't randomly assign juveniles who are accused of a very serious offense. You can't just draw a number and be like, hey, if we draw your number, you're going to adult court. And if we don't draw your number, lucky you can be tried in juvenile court. That would not be very ethical, and I can't imagine a circumstance under which that would be legal or permissible. So what researchers might do is say, okay, we already know we have this group of juveniles who are accused of whatever serious offense, and they have been transferred to adult court. We want to compare what happens to them, what the outcome of their proceeding is, with the outcome of what happens to similar juveniles who are adjudicated in the juvenile system. So what they'll do is they'll say, okay, we want to try to match them as closely as we can on some important characteristics. So there are a couple of strategies for doing this. First, they can look at the transferred juveniles and say, okay, we're going to match them kid for kid. So let's look at the first juvenile who was transferred in our sample. He was a 15-year-old male accused of, let's say, rape with whatever the prior record was. So then they would say, okay, we want to find a 15-year-old male accused of rape with a similar or the same prior record who is in juvenile court. Okay, now we're going to look at the second juvenile. This kid was 16 years old, accused of homicide. This is the prior record, and it was a male. So then they'll go to the juvenile court and say, okay, we need a 16-year-old male accused of homicide retained in juvenile court with the same prior record. So they try to match based on the important variables. So even though it's not random assignment and not everything is controlled for, the researcher can say, look, when it comes to the important stuff, gender, prior record, the crime, age, we have a pretty closely matched, we have closely matched samples. But the selection of the kids in that juvenile system in that sample was based on who was in the transferred sample. So that's why it's dependent, because the selection of kids into the second sample depended on who was in that first sample. The other way of doing a matched pairs design would be to say, okay, we have this sample of transferred juveniles. The average age of this entire sample was 16.24. So now we need to look at this sample of juveniles who were retained in juvenile court and make sure that their mean age was about the same, because you wouldn't want to have an average age in the first group of 16.24 and then an average age of like 14.9 in the juvenile sample, because that age difference is too big. If they said, okay, well, 78% of the kids in the transferred sample were boys, then they would need a similar distribution on gender in the juvenile sample. So that's just an aggregated approach. So instead of saying we're going to match kid for kid on these characteristics, an aggregate approach is just saying, what is the average age in this sample? What is the proportion of boys to girls in this sample? And they try to match it in terms of the overall statistics rather than kid for kid. But in any case, it's part of the same design called a matched pair design. The second dependent sample is a repeated measures design. And this is where you have pre and post scores in the same sample. And oftentimes this design is used when researchers are trying to test the effectiveness of an intervention. So sticking with the transfer example, in 1996, Pennsylvania passed a law called, I think it was called Act 36, and that was their transfer law. And it made it a lot easier for juveniles to be transferred to adult court. And this was very common at the time. So the whole purpose of these transfer laws, or the big purpose, was to have a general deterrent effect on juvenile violent crime. So there was this idea of, if we start putting kids in adult court, we're going to scare them, and they're not going to want to commit violent crimes, because they're going to know they're going to end up in adult court. So that then, researchers said, okay, let's look at these laws. Did they have that desired effect? And they looked at individual state laws. So if I was interested in studying Act 36, which I believe was the name of Pennsylvania's, it was passed in 96, then I would look at juvenile violent crime rates in Pennsylvania in the months prior to, it was March of 96 when it passed. So I would look at, let's say, 5 years. So 5 years times 12 months in a year would be, I would have 60 months of data prior to the transfer law, and say, okay, let's look at the trend of juvenile violent crime. And then I would say, okay, what happened after March of 1996? And I would look at another 60 months or 5 years of data and say, okay, between 96 and 2001, what happened to juvenile violent crime? Did it abruptly decline? Did it stay the same? Did it increase? Did it stay the same and then decline? Did it gradually decline? And I would look at overall trends in juvenile violent crime. But my observations at a later period in time were dependent upon observations earlier in time. You're using scores from the same sample. It's just a difference of whether or not you're analyzing scores from prior to this intervention or after the intervention. You can look at the effect of a boot camp program or a new community corrections program or the development of a new technology. Does that affect probationers who flee if they have, a GPS tracking type device on them? So anytime you're looking at the effectiveness of an intervention, where you're looking at the observations in your sample are before and after, so essentially your two samples are prior to an intervention and after an intervention, that is a dependent sample, and it's referred to as a repeated measures design. Your book talks about one and two-tailed tests, and a good way to remember the difference, and I think I talked about this last week, is that if you have a specific prediction, in other words, about the direction of the relationship between your variables, which often we do. So think about most of our research, especially if you're using statistics to test the relationship, it's probably theory-driven deductive research. So if you have a hypothesis coming from a theory, it's probably going to have a direction. In other words, let's say differential association theory that says, part of it says that juvenile delinquency is in part caused by juveniles who hang out with delinquent others. So you wouldn't just say, well, juveniles who hang out with, you wouldn't say that you expect there to be a relationship between who kids hang out with and delinquency. You know more than that. The theory says that juveniles who hang out with delinquent others are more likely to commit delinquency than juveniles who do not hang out with delinquent others. And that's a pretty simplistic interpretation of the theory, but for our purposes, it's fine. So the direction is part of the hypothesis. You're not just saying there's a relationship, but you don't really know what the relationship is. You're saying there's a relationship, and I think that it's a positive relationship. The more kids hang out with delinquent others, the more likely they are to commit delinquency. So if I say that I expect people who are conservative to be more supportive of capital punishment, I'm stating a direction. It's not that I just think, well, I bet political ideology is going to influence attitudes toward capital punishment. I'm not just saying that there's going to be an influence. I'm saying that more conservative people are probably going to be more likely to support capital punishment. I'm stating the direction of the relationship. So if you're stating the direction of a relationship, which in our discipline, more often than not, we do that. In theory-driven research, the theory tells us this is the way we expect these variables to be related, and this is why we have this expectation. But you should definitely still be familiar with two-tailed tests, both conceptually and also there are times that we use them. And there are times where we might be testing something that we don't know as much about, or that isn't strongly rooted in a theory that was set up to be tested. Or you might be looking at competing theories which produce competing hypotheses. One theory says that we expect this relationship to exist, and another theory predicts something different. So there are certain circumstances under which we would use two-tailed tests. So you definitely need to understand the difference between those and know when to use which test. But just again, I think the easy way to remember the difference is if it's a straightforward test of a theory or a statement about a relationship between two variables and you're predicting the direction of the relationship, then it's a one-tailed test. If it's not, then use a two-tailed test. So the example I'm going to use is this. I'm going to say that I have a sample of everybody in my sample is non-whites who were convicted of assault. So remember, those are constants. Everybody in my sample is non-white, so that is not a variable. It doesn't change. Everyone in the sample is non-white. Everybody in the sample was convicted of assault, so that is not a variable. What were they convicted of? There's no variation. Everybody was convicted of assault. So my sample is non-whites convicted of assault. My question is, does the mean sentence length, which I'm going to measure in months, so it's interval ratio level, differ between men and women? So among non-whites convicted of assault, does the mean sentence length in months differ between men and women? So think about that. What is my independent variable and what is my dependent variable? I am looking at whether the sentence length in months is different between men and women. Hopefully you got that the independent variable was gender, which I would measure as male, female, so it's categorical. And my dependent variable is sentence length, which I measure in months. So that's interval ratio level, which makes a t-test appropriate because I have a 2-category independent variable and a continuous dependent variable. The 5 steps, and we went through these with the chi-square test, those start on page 239 of your book for the t-test. They're pretty similar to the chi-square test that we ran, just different formulas, different numbers you're plugging in, but the general steps are still pretty much the same. So first you're going to state the null, this is step 1, state the null and alternative hypotheses, this time in terms of population means. In other words, the way that you state those will depend on what test you're running. So my null hypothesis, H sub 0, is that the sentence length for non-whites convicted of assault is the same for men as it is for women. In other words, there is no difference between the two. Gender does not predict sentence length. The sentence length is the same, or if it's not the same, then it's just a product of sampling error, which is random. It's not, any difference in the mean is not a result of gender. My research or alternative hypothesis, H sub 1, is the sentence length for non-white males convicted of assault is greater than it is for non-white females who are convicted of assault. And I specified the direction. I said that I think that men are going to get a longer sentence than women. I'm not just saying that I bet someone's going to get the longer sentence. I think gender is going to matter. I'm saying I think men are going to get the longer sentence. So since I specified the direction, we're going to do a one-tailed test. Step 2, you identify the distribution and compute the degrees of freedom. So I'm going to use the pooled variance t-test. The degrees of freedom is you take sample size, the sample size of the first sample plus the sample size of the second sample and subtract 2. So the sample size, and remember, once you designate a sample as sample 1 and sample 2, and it doesn't matter when you start which you designate as which, like males can be sample 1 and females sample 2, or females can be sample 1 and males can be sample 2. That doesn't matter. But once you make that decision at the beginning, you need to carry it through the entire test. So I'm going to say that males are my sample 1 and females are my sample 2. So since I'm adding, it's not that relevant here. So I'm going to take N1 plus N2, sample size 1 plus sample size 2 minus 2. So I'm going to say that I have 165 males in my sample and 120 females in my sample. So 165 plus 120 is 285 minus 2 is 283. So that's the degrees of freedom. I've now completed step 2. It was a very simple addition and subtraction. You can do that in your head. Step 3, identify the critical value and state the decision rule. Appendix C has the t-distribution. This is in your book. Has the t-distribution for a one-tailed test. Since the degrees of freedom, which I just computed, and it was 283, is greater than 120, which is the last number on the chart, I'm going to use the highest degrees of freedom at the 0.05 level, which I went over that last week, which gives me a critical value of 1.960. And since I'm doing a one-tailed test, it just has a positive sign. And your book talks about how if you have a two-tailed test, the direction can go either way. So you would need to have a plus or minus 1.96. But since my test is going to be a one-tailed test because I predicted which direction the relationship would be, then I'm going to, the 1.96, it's positive. So you don't need to worry about the positive or negative if you're doing a one-tailed test. And again, your book talks about that as well. So the decision rule is this. If my obtained t-value, remember we did this last week with chi-square, but instead of obtained chi-square, it's the obtained t-value, is greater than 1.960, which is the critical value, then the null hypothesis is rejected and our hypothesis is supported. So we need to calculate the t-value. If it's greater than 1.96, then we reject the null and say that our hypothesis was supported. If it is less than or equal to 1.960, then we cannot reject the null, and we would say that there's no relationship between the independent and dependent variable. Step 4, you calculate the obtained value of the test statistics. So here, the t-test. The last time you were calculating the value of chi-square. Okay, so the formula again it seems complicated. Take it step by step. I'm not going to go over every step of it because it's just, I don't want to say it's going to confuse you, but the numbers aren't going to be that meaningful to you because you're not actually doing the calculation of my example, but I'll tell you what I did, like just to give you an idea. So you have the information you need to plug the numbers into the formula. So for my first sample, which is the males, it's, remember, non-white males convicted of assault. The mean sentence length I have is 61 months. S1 is 2.15, N1, the sample size is 165, which I already told you. In my second sample, which are the females, so these are non-white females convicted of assault, the mean sentence length is 57 months. So we see that there's a 4-month difference in the sentence, and we see that men have a 4-month longer sentence than women do, but we don't know whether that difference is statistically significant. Is it a result of just random sampling error, or is it a result of actual gender differences? And that's what we need to find out. Is this difference statistically significant? Because we do see that a difference exists. So the mean sentence length for females is 57 months, S2 is 2.50, and N2 is 120. And these numbers would be given to you, or you would just know. You would know your own sample size. So then you just plug in the numbers, and you start with the formula with the 2 square roots. So it's the square root of like N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over the degrees of freedom. And then, you start by squaring the 2.15 and the 2.5, the S1 and the S2. So you square those, then you multiply by the N minus 1. Then you add those two things together, and then you divide by the degrees of freedom, and then you take the square root. And then you multiply by that other square root, which is N1 plus N2 over N1 times N2. So you add the top, you multiply the bottom, then you do the division, and then you take the square root. So now you end up with the square root of one number and the square root of the other. You take those square roots, you get the two numbers, and then you multiply those together. So I ended up with the square root of 5.31 times the square root of 0.014. The square root of 5.31 is 2.3, and the square root of 0.014 is 0.118. So 2.30 times 0.118 equals 0.271. You are not done though. That number gets plugged into a different formula. So you do like this kind of complex formula to get a number for another formula. And by complex, I don't mean difficult. I just mean it involves a lot of steps, but all the steps are basic arithmetic. So you end up with that 0.271, and it becomes the denominator of that other formula. So then you take N1 minus N2, so in my case it's 165 minus 120 over that number, which was 0.271. So 165 minus 120 is 45, divided by 0.271 is 166.05. That is the obtained value of t for me, 166.05. So at this point, I make a decision about the null. This is step 5, and state the substantive conclusion. Since my obtained value of t is greater than 1.960, so 166 is quite clearly greater than 1.96, I'm going to reject the null and say that my hypothesis that non-white males convicted of assault receive higher sentences than non-white females convicted of assault is supported. And that's where I can end the steps. The remainder of this chapter looks at scenarios under which you would use different t-tests. Just make sure that you're familiar, and it goes through the 5 steps, I think, for most, if not all of those scenarios. So just make sure you know what you would do when you would use each scenario, what you do differently, like if you have a two-tailed test, having the plus and minus, then you would have, you know, you wouldn't just, your rule is different. So if your obtained value of t, where I said if it's greater than 1.96, it would be if it's greater than 1.96 or less, less than on the other end. So you would, the rule becomes more strict for the two-tailed test. And then, like I said, your book talks about other different types of t-tests that you would use in different scenarios. Just make sure that you have a general idea of when you would use which test. But hopefully, you know, my explanation of this one and taking you through the 5 steps makes it a little bit easier and less intimidating to follow what the book is talking about. But if you need me to provide additional information or review in more detail all those other specific tests, I can do that. Just let me know. And if you want me, you know, if you need additional help, if you want me to take you through another problem, if you want me to go through another 5-step example, if you think that stuff would be helpful to you, please let me know. I'm trying to not overwhelm you with information because I know that you're busy, and if you do think you're getting it from the book and you're practicing the problems, I certainly don't want to confuse you or waste your time. But at the same time, I don't want to provide too little information where you're looking for more reinforcement and you're not getting it. So I'm trying to find that balance, but if you need me to go one way or the other, provide less or provide more, please let me know. And, you know, I'm happy to help however I can.